All right, so we're going to take a look at the first type of nuclear reaction, and that is called nuclear fission. There are two types of nuclear reaction. There's fission and fusion. All right, so we're going to look at fission first. Fission is most commonly found in early nuclear weapons. I can't even spell nuclear. I've got no idea how to spell nuclear, actually. It's pronounced nuclear. Yep, that's right. And this is found in nuclear power plants. All right, so fission means to split. So here's what happens when we do a fission reaction. Okay, so you start with, this is the common one that's used in some nuclear power plants. It's uranium-235, so we've got uranium-235 here. I'm going to zoom in. Uranium-235 has this roughly stable nucleus. You shoot a neutron at it. It becomes uranium-236. Uranium-236 is an unstable nucleus, so it is going to decay. It decays into a krypton nucleus and a barium nucleus. It releases some energy as gamma radiation, and it also releases 3 high-energy neutrons. All right, so this one neutron imparted a little bit of energy into this. This one neutron had a little bit of energy, but out of the end, you got a lot of energy. Okay, so you only input a little bit of energy, and you get out a lot of energy. How do you get out this energy? Well, this energy comes out as the speed of these guys go flying away really fast. The gamma rays have energy, and these neutrons go flying away really fast. They have energy. So you're putting in a little bit of energy here, and you're getting out a lot of energy out of here. That's perfect. We can use that energy, can't we? So this is the general reaction. Now, some numbers. All right, so in general, you get about, so the total exit energy, total energy out is about 200 mega electron volts. That's the total energy out. Now, I do not know the energy in. I'm going to just see if I can find it. You need to put in about 7 to 8 mega electron volts. So energy in is about 7 mega electron. It's a small e. So as you can see here, you put a little bit of energy in, you get a lot of energy out. So you need to put in about 7 mega electron volts, and you get energy out of about 200 mega electron volts. It's right here. Haha, I was wrong. For uranium-232, it's only about 1 mega electron volt. For uranium-235. For uranium-235, it's only about 1 mega electron volts. So we'll see why that's important in a little bit. So how is all this energy released? So you got 1 megavolt of energy into this 235 atom, becomes unstable, and it produces about 200 mega electron volts coming out. So where does that energy show up? About, for this guy and this guy. So 1 and 2 have a total of about 169 mega electron volts of kinetic energy. Kinetic energy is energy of motion. That there, it means they're moving. These guys move at about 3% the speed of light. 3% the speed of light. That's pretty fast. So that's about 170 megavolts, mega electron volts of the energy. The neutrons, they have, each neutron has about 2 mega electron volts. So each of those neutrons has about 2 mega electron volts. And you get about 7 mega electron volts in gamma rays. Gamma rays. Now, I don't know if that adds up. It doesn't quite add up. I'm not sure where the rest goes. So the rest goes out as more kinetic energy of fission fragments. So kinetic energy of these guys. So these neutrons would have even more energy than just the 2 mega electron volts. Okay, so that's what happens. Now, so we start with a neutron with 1 mega electron volts hitting a U-235 nucleus, creating an unstable nucleus here. The unstable nucleus decays like this. It releases a krypton, a barium that are traveling fast, a bunch of neutrons that have a lot of energy, and a bunch of gamma rays. Now, all this energy, if you absorb it into something, it can make something very hot very quickly, which is how you produce power with this. All right, now, what happens to these 3 neutrons? Well, these 3 neutrons can go and hit another U-235 atom. So kind of looks like this. So we start with a neutron. And it hits a U-235. Then this fissions. We're not going to care about these fission particles. More importantly, this can make 1, 2, 3 more neutrons. And what can these neutrons do? Well, if there's another uranium-235, what's going to happen? Well, these guys are all going to fission. And what are they going to do? This guy's going to release 3 more neutrons. This guy's going to release this guy in the middle is going to release 3 more neutrons. This guy on top is going to release 3 more neutrons. This is going to get out of control really quick. This is an uncontrolled chain reaction. And if you get this to happen, boom. Mushroom cloud. This is how you get a nuclear explosion. You do not want this to happen. You really don't want this to happen. So in a nuclear power plant, you don't want an uncontrolled chain reaction. You want it so that 2 of these neutrons get absorbed, and only 1 of these neutrons is used for another fusion. You want to be able to control how many neutrons are being used at once. Okay, so in a nuclear power plant, you have to be able to control the number of neutrons that are causing new fission reactions. All right, so as you can see here, our energy efficiency, like we're getting out 200 times more energy than we put in, which is great because you get out a lot of energy. And you start with a stable, relatively stable uranium-235 atom, throw a neutron on it, unstable, releases a couple of new atoms, new nuclei, that are traveling very quick, 3% the speed of light, 3 neutrons, and some gamma rays. If these 3 neutrons go on to hit other atoms of uranium-235, you are going to get an uncontrolled chain reaction, which is a boom. You don't want a boom. Well, sometimes you do, but in a nuclear power plant, you need to control the neutron emission. Now, you're only going to get a nuclear explosion if you have a critical mass, a large enough amount. So if you don't have a critical mass, so a critical mass is a certain weight of fissile material. If you don't have the critical mass to get a nuclear explosion, you can just get a meltdown. That's kind of what happened in Chernobyl. In Chernobyl, when they shut down the safety systems to run their experiment on their automatic refueling system. Okay, those safety systems caused an error, and they got a little bit of a meltdown. So they got an uncontrolled chain reaction. So you got an uncontrolled chain reaction, but they did not have a critical mass of uranium-235 in the reactor core. You don't keep a critical mass of U-235 in there. So they got an uncontrolled chain reaction, which led to a meltdown. That meltdown led to a whole bunch of heat. That heat caused a steam explosion. So the explosion in Chernobyl was not a nuclear explosion caused by a critical mass of uranium. It was a meltdown which caused an excess amount of heat. That excess amount of heat caused a bunch of water to turn into steam really quickly. That water turning into steam really quickly was the explosion. So that's what nuclear fission is. Fission means splitting apart. And we start with a 235, hit it with a neutron so it becomes unstable. It splits apart. We get all of these Items coming off, krypton, barium. They're both traveling really fast. Gamma rays and neutrons. And you don't want those neutrons to get out of control. If you have a critical mass, you'll get a nuclear explosion. If you don't have a critical mass, it'll just melt everything down. It'll just go until it's hot and it melts. And you just have an uncontrolled